Good afternoon, guys. Uh, I'm going to discuss uh, about consumption allowance. So the vessel is loading in Montreal, Canada, and going to discharge in Cartagena, in Colombia. So let's start, guys. Okay. Okay. So the vessel is going to load in Montreal, Canada, and he's uh, going out to sea. Okay, so this will be his route, passing Quebec and going out to the open sea, and he's going to load discharge in Montreal, in Cartagena, in Colombia. Okay, guys. So from here, he will go. He will go. Sorry. So from here in Montreal, Canada, he will go to Colombia. He will go past to Bermuda and probably crossing to Cuba, and here it is Colombia. Okay, so that is where he is going to discharge. Okay, and from Colombia, going to Cartagena, which is here. This is Colombia, this is Nicaragua, and Guatemala. So he's going to discharge in Cartagena. Okay. Then we go to the problem. So the name of the vessel is Mbinara, and it's going to load in Montreal, in Canada, and going to discharge in Cartagena in Colombia. So during the winter season, the North Atlantic winter seasonal zone commences on November 1. Okay, so distance to reach open sea from Montreal is 428 nautical miles, and Nara streams at 11 knots. Okay, this will be his remaining on board. FO is 1387, DO is 21 metric tons, LO is 41 metric tons, freshwater is 255, ballast is 0, constant is 255, and the consumption from Port of Montreal to reach the open sea is fuel oil is 25 metric tons per day, and the diesel oil is 0.5 metric tons per day, and fresh water is 4 metric tons per day. Okay, so remember, guys, the distance from open sea, from Montreal port to open sea is 428 nautical miles with a speed of 11 knots. Okay, so here's the problem. It says find the quantity of cargo to load at Montreal or loading port, the maximum permissible draft if she is floating in a water density of 1.025, meaning what will be his draft when she is floating, or departure draft when she is floating in 1.025, 1.005, and her draft in which she proceeds to see a density of 1.025. Okay, now if she is about to complete loading at 9.36, okay, in water density, what will be is about to complete loading at a drop of 9.36 in water density 1.025. Find the quantity of cargo to remain to load. Okay, so 9.36. Okay, proceed. Okay, solution: determine the governing zone. The governing zone is winter zone. Okay, so let's check. According to him, it's a winter zone because it's starts at November 1. Okay, so where do you find this one? We go to uh, where's that? Winter zone. Let me see the winter zone. Winter zone. I think I deleted it already. Let me check, guys. Where's the winter zone? Okay, let me check, guys. Zone here. We go here. Winter zone. Here. So winter zone is says winter November 1 to November to 31 March. So it starts from November 1. So Montreal, Canada is somewhere here. So he is in the winter zone when it starts on November 1. Okay. Okay, let me see this one. Okay. Okay. Then we go to number 2. Consumption calculation. So daily consumption of FO is 25 tons. Daily consumption of DO is 0.5 tons and freshwater consumption is 4 tons, 4 metric tons. Okay? So total consumption is 29.5 metric tons. And number of days steaming of 1.6 days, meaning what he meant is from the loading port Montreal is 426 to the open sea is 426 miles, meaning if you divide 428 metric tons by the speed of 11 knots, then your steaming time will be 1.6 days. Okay, so with 1.6 days, multiply it with your daily consumption of 29.5, then you will have total consumptions of 47.2 metric tons. Okay, so I repeat, how did you get this 1.6 days? That will be 428 nautical miles from the loading port to the open sea. You divide it by the speed of your vessel, which is 11 knots, then you will get the steaming time of 1.6 days. Okay, since you have a total consumption per day of 29.5 metric tons, you multiply this total of consumption per day by your steaming time of 1.6 days. That will, you have a total consumption of 47.2 metric tons from loading port of Montreal to the open sea. Okay, that will be your total consumption. Now, with your remaining on board from your departure at Montreal, your fuel on board will be 1387 metric tons. Diesel will be 21 tons. Lube oil will be 14 tons. Fresh water will be 255 tons. Your ballast is 0 and constant is 255. Your total weights or non-cargo weights will be 1932 metric tons. Okay, so that will be your non-cargo weights. So now we go to the next. Now the winter displacement, which is 301183, okay, which is this one, guys. Winter displacement is this one, 30183, okay, and the corresponding drop is 9.351. Okay, so we concentrate on this displacement of 30183. Okay, and with this is one. So you add the consumable allowance, which is 47 tons. This will be your true displacement of 30230. Okay, then you less this one with your light ship or light displacement, which is 6772, which is this one, guys. Your light ship is 6772. This is your light displacement or light ship, or 6772. Okay, which is this one, guys. So less this one, this will be your dead weight of 23453 minus your weight on board of 1932, which is this one, guys, 1932. Your non-cargo weights, okay, and you less this one, this should be your maximum cargo to load. So your maximum cargo to load is 21479 metric tons. Okay, so we go to number 4. Know the drop displacement at limiting zone, meaning your salt water departure of the winter drop is 9364 and the displacement is 30230. Okay, this will be your winter displacement of salt water. This will be your limiting zone. So this should be your displacement if you are to depart at Montreal. So that will be 9.364. We'll check this way. Winter limiting zone. Winter limiting zone. I'm sorry. Winter limiting zone. Winter. And your this drop should be 351. Okay. That will be your winter 351. But what we have here is, according to his, he got only 9.364. This should be 351, but he made it here 964. Why 964? I know, no. This is correct because your true displacement is 302230, which is this one. This corresponding drop will be 364. Okay, we'll check, guys. I will prove it to you why he got this 364. 3030. Go here to number 7, then 30230. What is 30230? Which is this one, guys. 30230. Then we put this enter. Then 364, 9.364. Okay. That's why he got here 9.364, okay? But this is salt water. We should be sailing in a tax density 1.025, 1.005. Okay, guys, let's go back with this one first, so the I can back to normal. So we go here. So, but this is a winter drop or winter displacement. But what if our density is 1.02, 1.005? This should be the local density that when you are going to depart at Montreal. So this is the formula, guys, to get the displacement of 1.005. Okay, so the actual displacement times the constant of 1.025 of salt water over or divide by the present density or duck water density. So transpose, actual displacement is this one, 30230 times your constant of density of 1.025 of salt water over your duck water density or present density is 1.005, and this will be your corresponding displacement of 308316. So what will be the corresponding departure? What will be the departure drop with this displacement? That will be 9.535. So we'll check 308316, 308316, 308, Oh, I'm sorry. Ano na yun? 316. 331.6. Enter. That will be 535, 9.535. Okay? Get there. 9.535. Okay? That will be your departure draft. That will be your departure draft in density 1.025. Okay? Okay. And then, please, I want to back to normal. Okay. Is that correct? Another. Oh, sorry. Never mind. So now let's go to form number 6. We will try to compute this one, guys. So this will be your maximum departure drop of 9.535. Okay, but according to this is your departure drop, okay, of 1.005 density. But according to the problem here, when you reach the drop of 9.36 in density of 1.005, what will be your remaining cargo to load? Okay, so when you reach a drop of 9.36 in a density of 1.005, what will be your remaining cargo to load? Okay, so 9.36, put this, guys, 9.36, we go to small, and this is what you call the how to find trim when handling several weights. Okay, so you put here 9.36 this is your actual draft forward enough. Okay, when you 9.36. This is when the foreman and the chief officer has stopped the loading to drop check for the remaining cargo to load, and you both agreed that forward drop will be 9.36 and up drop will be 9.36 and your mid port will be 9.36 and your mid starboard will be 9.36. Okay, and take note guys that your departure drop in 1.005 should be 9.535. This will be your departure drop in a density of 1.005. So we put this 9.535, 9.535. Then you will have a sinkage of 175. Okay, this will be your sinkage of 175. Check what is this sinkage. 175. That is your sinkage of 175. Okay, so 535 minus 9.35 is 175. This will be 9.535 is your departure draft, and 9.36 is the draft which you stop loading because the chief officer and the data surveyor is going to make a draft check around the vessel to compute how much remaining cargo to load. Okay, so this will be your sinkage of 0.175 centimeters or meters. Okay, and according to his formula, sinkage times TPC times 100 times present density over 1.025 is 600 tons. And this is the conversion, guys. Okay, now this is his formula. Okay, look at mine. Sinkage is 175 or 0.175 centimeters. To get the remaining cargo to load, this is the formula. Okay, and that will be K8. What is K? And 8 will be the sinkage times 100 times M3. What is M3? Is M and 3. This will be this TPC of 35.45. How do I get this TPC? With the final departure drop of 9.535, you have to get the interpolation of TPC. This already run up. That will be exactly 35.45. That will be your TPC. So this will be M3. So again, K8 is the sinkage times 100 constant times your M3, which is 35. Then we have a value of 620.4. Okay, TPC is 35.45. What is this TPC? TPC is 35.52, but I have 35.45. Okay, why did I get 620? This is the value, but this got here is 629. Okay, anyway, I just proceed with my program. Since this is your sinkage of 1.175, we'll check if we'll get that. So 120, 620, 620, put this enter. Bakit naging 620 yan? 175. That will be what, 75? Okay. 620, that will be almost, this will be almost 175 here, and 9.55, which is almost here. Okay. Say, let's make it exactly 620.4. Okay. There. See? If you put exactly the amount of, from here, follow the arrow here, 620.4, what it will result if you put 620.4, that will be exactly 175. 175 here, and 6535 here, exactly. And this is the recommended cargo to load. So here you have 609. No, it should be 620, but here he added this value of 1.025, or the density. But here I take out this one, but I still get the figures here. Okay. Now let's check. Now, since the recommended cargo to load of 6220, what will be his departure drop? So we go to trim 2 holds. I got here 620, and I got here holds 1 and 4. And here the remaining cargo to load is 620.4. What will be I load in hold number 1? Let's say I have a list of 50 centimeters. Okay. And what will be I load in hold number 1? That will be 43. Okay, I put here 43. 43. And number 4 will be 577. 577. Okay. And what will be my departure drop? My departure drop would be, forward will be 9.29, up will be 9.79. I have a trim of 50 centimeters, and mean drop of 5.36, which is almost. And here the mid drop and mean drop is 535, and I have a 0 deflection. So we go to the other program, which is this one, which is how to find trim when handling several weights. Okay, remember that the surveyor chief officer, upon stopping at the drop of 9.36, and they have a departure drop of 9.35, we have a load of our remaining cargo total of 620.4, and you're going to load it in 1 and 4, and you have number 1 is 43, number 4 is 577.4, and your departure drop forward will be 5.29, 9.29, up will be 9.79. You have a centimeters of trim, 50 centimeters trim, and your main drop is 9.54, which are 9.55, 6 here, and main drop is 9.5, and you have a 0 deflection. Okay, guys. But look, guys, here, take note that since your case is 0.175 centimeters, your remaining cargo to load should be 6.20.4. but he, according to his computation here, is 609. Why? Because he added this figure, okay? Which the formula, the real formula is you don't have to need to add this, the present density of 1.005, okay? And he got this 3552. What were you? 3552. Density of 3552. Let's check this one. 3552. 3552. That will be more. How much did it say here? I'm sorry. How much did it say? 9365. Okay. 9365. We'll check here. 9365. 93365. Oh, 635, huh? I think 635. 635, okay? 635. 635. 3552. But if you put here, if your TPC is 3552, which is this one, and your remaining cargo to load should be 976, is very far. So it should be like this, guys. If your your sinkage is 175, so your remaining cargo to load should be 620. Okay, and your departure drop would be forward is 9 point. No, say if you say you want to, you have an even trim, you want to have an even trim. Okay, put here 0, and what will be you load in forward? 258. Okay, put here 258. 258. Up will be 364, 362, 362. There, and your drop would be forward will be 0.94. Up will be 93 of 0 deflection, 0 trim, and your mean will be 535. You have the 0 deflection here. Then we go to the other formula, other program, which is how to find trim when handling several weights, and you load in number 1 of 258 here, and number 4 is 362.4. Your departure drop would be 9.54, 9.54, 0 trim, and your mean will be 535, and you have a 0 deflection here. Okay, so it is the right to load of 964 if we have a trim of our sinkage of 1.75, which he has here 1.175, but you will never get this value of 609, and you will never use this present density 1.005, which is this one. Okay, guys, so that's it, guys. I hope you would appreciate this program that I have. Okay, if you like this video, please click the like button, share, and subscribe, and don't forget to click the notification bell. Okay, thank you very much for watching, and have a good day. Hi guys, uh, I'm going to show you a program which I make, which I made. Now, I'm going to talk about this in number 5. Find the departure draft of black water density. So, this formula, guys, which says look up displacement, meaning the formula says actual displacement, which is displacement or your departure of saltwater displacement is 30230 metric tons, which is this one, guys, times your saltwater density, which is constant, this one, over your present water density or your local density, which is 1.025. And the answer to this formula is 30831.6. Okay, that will be the displacement when you're floating in 1.005 your density, and this is your departure density. Okay, this will be your departure displacement when you are floating in a density 1.005. So what will be the drop of this displacement? The corresponding drop of this displacement is 9535. Okay, which I have already shown you before. But I have another solution to this one. This is much simpler, but I made it in Excel, which is very quick to use. Okay, so let's start, guys. I go to my program. This is my program, which is your conversion of density. So this side part will be salt water to density. Okay, our displacement, for example, was 30230, which is this one, 30230. Okay, and the corresponding drop was 9.36. Okay, 9.364. Okay, let's put it 9.364. Put this 9.364. There you have 9.364, and the departure density was 1.005, and the saltwater constant is 1.025. Okay, and this is the formula, guys, which I made, and that will be the displacement times your displacement times your salt water times the water, which is the same, guys. Look at here. Here, displacement times salt water. Okay, look here. This displacement times salt water 1.025 over your duck water density, which is this one. Actually, it's the same, guys. So you transpose it. When you transpose, that will be density displacement of 302.30 times your saltwater 1.025 over 1.005, which is the same, guys. Here, 30230 times 1.025 over 1.005, which is the same, guys, here. See? 30230 times 1.025 over 1.005. So that the answer would that be 30831.59, and here you have 30831.6. It's already run off, but in my program it's already not yet run out, but I run up to 30832, and the corresponding drop will be 9.535. which is this one, guys, 9535. Okay, we'll just show you in the program. Okay, show you in the program how I got it. Okay, bear with me, guys, bear with me. And let's see. Sorry. Uh, uh, Safety. And we go to here, 7. What's the I'm sorry. It says 30832. 30832. 30832. Put here 30832. Is that correct? 30832. Just want to confirm, guys. 30832. Okay? 30832. 30832. What will be his drop? And the drop is the same. 9.535. 9.5 9.535. Here you got a drop of 9.535, and here you got 9.535. Okay, now take note of this program that I made. This is from salt water to dark water, so we reverse it. So now we go the other side. We have dark water to salt water. Okay, so asking for the dark water displacement, which is 30832, which is this one, and the drop would be 535, and dark water density is 1.05, and you have constant of 1.025. We have the same formula, and the answer would be in salt water will be 30230, which is this one, 30230, and the drop would be 9.364. 9.364. Okay, so we put this one to put this one to okay, 9.364. Okay, so it's only the reverse. So what I made is only for short computation. So you can use this program. You can also use this formula. What's the same? What I made is only by Excel to make it more quick. You just put this displacement, the mean drop, the water density, the salt water density. Then once you already place that, you will have the answers right away here. So with the dark water to salt water, you put the displacement, the drop, the present density, and the salt water density, and you will have the same answer here. So this is what I'm going to show you guys. So thank you for watching, and have a good day. Okay, thank you. Stop.